Hey everybody, it's Mr. Robeson here. We're working on statistics today, and today we're going to look at two-way tables and conditional probability. So conditional probability is usually where it starts getting a little trickier, so pay careful attention here today, guys. All right, so usually this is when I have you guys get up and collect some data in class and play a little trash get ball. We put the garbage can out there, and we take some tennis balls and see if we can hit the garbage can, and we usually play guys versus girls to see who can make more. But since we are distance learning this year, I made up some data. All right, so this is what happened. So we had males take shots, we had females take touch. We had a lot more of the lady folk in class than we do guys, and that is actually true. We do have a lot more girls on the roster than we do guys. And we had guys make 50 shots and miss 40 shots, 90 total shots. The girls made 110 shots, missed 70 shots out of 180 shots. So we had a total of 270 shots taken. All right, so now some questions about this. So we're organizing this in what's called a two-way table. We went over this the other day in class. One way of the table is measuring gender. The other way of the table is measuring whether you made or missed a shot. It's kind of like a Punnett square back in biology, or maybe you did factoring stuff by tables or multiplying two binomials by tables, like male and make would be 50, female and miss would be 70 because that's where they cross. That's how two-way tables work. We just organize the data that way. All right, so once we have that organized like this, what is the probability that a shot is taken by a male? Well, probability of male is, well, the total male shots were 90, and the total number of shots were 270, so it is 90 out of everybody, so out of 270. What is the probability that the shot is made? So the probability that we make a shot is, well, the total number of makes is 160 out of the total, so 160 out of 270. Remember, we don't have to reduce fractions. Number 3, what is the probability that a male makes a shot? All right, so this can kind of be interpreted two ways. I'm going to interpret it this way. So out of the males, so that means we're out of 90. How many shots did they make? All right, so that means the probability that a male makes would be 50 out of 90. All right. What is the probability that a female takes a shot? Just takes a shot. So the female shots would be 180 out of 270. What is the probability that a female makes a shot? Well, that's kind of like the male makes a shot back here. So we've got a female making a shot. So out of the females, there were 180 shots, and they made 110 of them. So the probability female and make would be 110 out of 180. What is the probability that a shot is made or is taken by a male? All right, so made shots are this one and this one. These aren't made, these aren't made. Taken by a male would be, okay, these ones, we've already counted them. Not these ones, but we're still counting them anyway because it's made. And these ones, all right, because it's male, and it said male or made. So this counts because it's male. This one is not male and it's not made, so we're not going to count this one. So the probability that we make a shot or that it's male that does the shooting is 50 plus 110 plus 40 out of the total. So this is still out of everybody because it didn't say, that it was out of only males or out of only females. So we add up this top, and it looks like we're going to get 200 out of 270. All right, let's try that again with this one. What's the probability that a shot is made or is taken by a female? All right, let me erase these. All right, so now we want made. So these guys are made. These guys are made. Or taken, these guys aren't made. These guys aren't made. Or taken by a female. Well, that's not these ones, but we're already going to count them. These ones, yep, we've already counted them. Not these ones, but these ones. So we got the 50, the 110, and the 70. So the probability that we make a shot or female is 50 plus 110 plus 70 out of 270. And if we add those up, I think we're getting everything except for the 40, so that should be 230 out of 270. All right, now a couple of those were tricky. They weren't out of 270. All right, we'll look at that some more later, but some more practice here on two-way tables. So finding probabilities of two-way table. Let's see, suppose we chose a student at random. Find the probability that the student has pierced ears. So let's see, we're looking at pierced ears and we're looking at gender. So we want to just know, do they have pierced ears? So that means yes for pierced ears. The total for that is 103. It's still out of everybody. So this probability is equal to 103 out of 178. Next up, what is the probability that the person chosen at random is male with pierced ears? All right, well, let's get rid of these two. We want male with pierced ears. So yes for pierced ears, yes for male. That's just these guys. It doesn't say or, it says a male with pierced ears. So it's just those 19. And it's still out of everybody. It doesn't say that given that they were male or given that they have pierced ears. It's still out of everybody. So it's still out of 178. Part C, we want the probability that they are male or has pierced ears. All right, so this is where it gets tricky. So for male, we'd count these guys and these guys. These guys we wouldn't count because they're female. For pierced ears, we'd count these guys, we've already got them, and these guys. But not these guys because they're female and they're no. So we'd add up these three sections. So that would be 84 plus 19 plus 71 out of everybody still, 178. All right, so there's the 103 out of 178. There's the 19. And if we add those up, let's see, we're adding up the same ones, 19, 71, 84. We get the same 174 out of 178. It's all of them except for these four right there. So we could have just subtracted 174 out of 178. All right. Actually, let's go back here. There is another way we could do this part C. And the way we could do, actually there's two other ways. One is we could do the subtraction. We could do the 7 out of 178 subtracted from everything. But another way we could do it is we could say, what's the total number with pierced ears? Well, it's 103. What's the total number of males? 90. Problem is, this 19 is being counted in both of these. So we could also do 103 plus 90 minus 19 out of 178. And if we add those up and then subtract the 19, we're going to get the same 174 out of 178. So that's another way we can do it. We can add up the two totals and then subtract the overlap. All right, so now some examples. What's the probability of someone having a dog? So here's a table. We've got having a dog or not having a dog. Clearly the people having a dog are much better people. We've got men, we've got women, and we've got some totals. So out of this whole table, what's the probability that someone has a dog? All right, well, the total number that have a dog is 120. All right, we're still out of everybody. So it'd be 120 out of 271. All right, what's the probability of someone having a dog or being a woman? Dog or woman. All right, so we can just go through. Did these people have a dog or are they a woman? Yeah, they have a dog. We count them. How about these people? Do they have a dog or are they a woman? Nope, they're man, they're no dog. We don't count them. How about these people? Yeah, they have both. We're definitely counting them. We're not going to count them twice, though, because they only exist once. Next up, these people. They don't have a dog, but they're a woman, so we're still going to count them. So we get 72 plus 48 plus 87 out of 271. And if we add those up, or we just subtract the 64, we're going to get, I believe it's 207 out of 271. All right, so now what is conditional probability? So we kind of snuck in a couple of them earlier there. The probability we assign to an event can change if we know that some other event has occurred. So something else is going to happen first, which may or may not change the probability of another event. All right, and when something else happens first, that means that the probability of the other thing happening is conditional on the other event having already happened. So suppose we know event A has happened. Then we can say, what's the probability of event B happening given that event A has happened? That is denoted by this. So this means that A happens first, even though it's listed second. And then we're asking, what's the probability now of B happening, given that A happened first? All right, so if we're talking about Skittles, maybe we took a Skittle out. It's going to change the total number of Skittles that are left. If we're talking about, say, okay, so yeah, this is read under the condition that, or given that. I usually just say given that. Given that is what the bar straight up and down means. So let's say we're looking at a deck of cards. All right, so if you don't know about a deck of cards, there are 4 queens, there's 4 kings, there's 4 aces, there's 4 jacks, there's 4 of each number of cards, and there's 52 total cards in the deck. So right now, the probability of getting a queen would be 4 out of 52. Sorry to put my 52 on top there. 4 out of 52 would be the probability of getting a queen, also would be the probability of getting a king. All right, but now, given that someone else removed 1 king from the deck, so that means the king here has happened already, he's been removed. Now, what's the probability of getting a queen? All right, well, the probability of getting a queen, given that a king has been removed from the deck is, well, there's still going to be 4 queens, but there's no longer going to be 52 cards in the deck because we took out a king. It's going to be 52 minus 1, the king that we removed. All right, so we're going to be 4 out of 51. All right, so you see how that the probability changed. It was 4 out of 52. Now it's 4 out of 51. All right, it's close to being the same as before, but it has changed. That first event, that taking a king out of the deck, affected that probability and changed it. That means these are what we call dependent events. I should probably write that down. We'll talk about that more in the next presentation. Dependent, the probability changed. Given that someone else removes 2 queens, what's the probability of getting a queen, given that 2 queens had already been taken out? So what's the probability of a queen, given that 2 queens have been removed? All right, well, there were 4 queens. We took out 2 of them, so what's left is 4 minus 2. There were 52 total cards. We took out 2 of them, so we're left with 50. So it's going to be 2 out of 50. Now, the trick here is not saying what's the probability of getting a queen, then probability of getting a queen, and then the probability of getting a third queen. It's just asking about the probability of getting a third queen. All right, so it's not doing it 3 times in a row. It's just asking about the third one here. All right, and notice the probability has changed again. So again, these are what we would call dependent events. The probability is changing. All right, so there is some other trickier, more complicated notation that we could use with this for conditional probability. So remember, probability of A given B, that means that B happens first. All right, so that is the probability that it'd be out of on the bottom. On the top, this is and. Probability of A and B, given that B has already happened. That's what's going on here. This is A and B. Here's our given that line, the fraction bar. That given that B happened already. All right, and you can also do it the other way around. If we flip it the other way, then here A has already happened first, and then we want the probability of both of them happening here, A and B, B and A. All right, so let's take a look at how we could do it just using the symbols and moving stuff around. So we're just dividing here. All right, suppose another class recorded their gender and took trash ball shots, but we don't have the table with their data. I just have some probabilities. We know that the probability of making and being male is 0.28, and that's out of everybody. Probability of just being male is 0.52. Probability of making and being female is 0.35. What's the probability of making given that they were male? Well, on the bottom is going to be the probability of male. On the top is going to be the probability of both. Make, intersect, male. Well, the probability of make and male, we've got right here, it's 0.28. Probability that they were male, we've got right there, it's 0.52. So this would be 0.28 out of 52, 0.52. All right, real quick, easy way to move that is just say 28 out of 52. Just move the decimals over 2 spots. There we go. All right, we could also just divide that if we wanted to and get a decimal answer. Let's see, 28 divided by 52 on my handy calculator here is 0.538. So that means the males made about 53.8% of their shots in total. Not bad. Find the probability of make given female. Well, that's going to be the probability of make and female. That's our symbol for and. It's the intersection symbol. Over the probability that they are female. All right, well, what's the probability that they're female? I don't see that listed up here. All right, but we do have probability of male, which would tell us that the probability of female would be 1 minus that, which would be 0.48. There's complement probabilities kicking in. So 0.48, and the probability of make and female is 0.35. If we were to divide those, 35 divided by 48, we get 0.729. Wow. From these made-up numbers, the ladies did really well here. Guys, what happened? All right, what about the probability of miss given male? Well, you could just say it's probably the complement of this, but let's see if we can figure it out. No, that's probably the best way to go about doing it. We could say it's the probability of miss and male over the probability male. All right, but we don't have the probability of them missing and being male. We could probably figure it out up here, but we're still just going to be like subtracting and doing some other stuff, or we could use what we did up here. All right, but it's probably easier to say it's 1 minus the probability of them making and being male. All right, because those two should be complements. All right, so that's 1 minus, here's the probability of making being male, 0.538, which gives us 0.462, I believe. All right, so complement probabilities, still useful. All right, how about here? Probability of missing, given that a female took the shot. Well, that would be 1 minus probability of making, given that a female took the shot. All right, because these two things are complements, we know the probability of making. It's going to be 1 minus 0.729, which equals let's see, that's going to be 271, 27% miss. Got a little tricky there, didn't it? All right, so most of the time we will not be doing it this way. So most of the time we won't have to memorize these formulas and do it this way. It's probably a good idea to know these formulas, but they are on the formula sheet for the AP exam. And most of the time they give you the two-way table and you can just read the numbers off the two-way table. I find that much easier than trying to find all these probabilities and remember all these symbols. So usually we're using a two-way table. We're not doing it like this. So if you don't like this, that's okay. We're not going to do it like this. All right, so here's our two-way table. Given that someone owns a dog, what is the probability that they were a man? All right, so if they say given that someone owns a dog, that means the only part of this table we are looking at are the dog owners. All right, so what's the probability that they were a man given that they owned a dog? All right, well, the total here is 120. All right, that's the total dog owners. And now we want both man and dog. So what's the probability of being both a man and a dog? Or how many of them are both a man and a dog? Well, that's 72. So it'd be 72 out of 120. Now, if we did this the other way, it'd be tricky. Like it would be, so this would be equal to probability of man and dog over the probability of dog, which would be, let's see, man and dog would be 72 out of 271. Dog would be the 120 out of 271. The 271s would cancel, but you'd have to know how to do that with fractions. And we get 72 out of 120, the same answer, just a lot more work. So like I said, I like to just kind of look at the chart and think my way through it. But if you like using the formulas and want to use the formulas, you can use the formulas. Both ways work. Next up, given that someone is a woman, that means we are only looking at the women here. So that means all the other numbers I'm just going to ignore. What is the probability that they do not have a dog? So do not have a dog. That's these guys, no dog. So it'd be the 87 out of 135. So that's how I do it my way. If you want to do it their way, the formulas, we want the probability of no dog, given that we've got a woman, which will equal the probability of no dog and woman over the probability of woman, the second thing. All right, so no dog and woman would be the 87 out of 271. Probability woman would be the 135 out of 271. The 271s are going to cancel, and we do in fact get the same 87 out of 135, but I feel like my way was much faster. Just look at the women. So there's our total, and say how many do not have a dog. There's 87, so it's 87 out of the total. All right, so that's it for conditional probability for now. We'll visit it later when we do some other rules later on, and we definitely will talk about it some more, and we'll definitely look at two-way tables some more. All right, there is one more video for 5.2. Hopefully I'll keep it short.